Good evening, everyone. My name is Claude Vru. I'm Professor of Forensic Science and Director of the UTS Centre for Forensic Science. I've got the great pleasure to be your MC tonight. First, welcome to this UTS Science in Focus, which is dedicated to illicit drugs. We're fighting a losing battle with Morgan Philp and Marie Morelato from the UTS Centre for Forensic Science. Before we officially start tonight's very fascinating talks, I'd like to acknowledge the Gadigal people of the Eora Nation upon whose ancestral lands our campus now stands. I would also like to pay respect to the elders, both past and present, acknowledging them as the traditional custodians of knowledge for this land. Tonight's speakers, Morgan and Marie, will be joined by Associate Professor Shanlin Fu, who is supervising Morgan's project here at UTS. The first speaker is Morgan Philp. So Morgan completed a Bachelor of Forensic Science in Applied Chemistry Honours at UTS in 2012. And then she took a year off, traveling and living abroad in the UK. And when she came back, she started a PhD in the Forensic Toxicology group at UTS under the supervision of Associate Professor Shanlin Fu. Morgan is currently in the last year of her PhD, and she's been developing presumptive tests for the detection of illicit drugs, specifically on new psychoactive substances such as synthetic cathinones. Her aim is to develop new methods and new test methods capable of detecting these compounds in a rapid and cost-effective manner by studying reactions that can take place with these drug molecules to produce visual changes. Her research will allow for the effective detection of new psychoactive substances that may currently be going undetected using current techniques. And I heard that no later than yesterday, Morgan and Shanlin were awarded a priming grant from the Austrian Academy of Technology and Engineering to pursue the technology presented tonight. So congratulations, Morgan and Shanlin, and please welcome Morgan.
Thank you, Claude, for that very kind introduction. And good evening, everyone. Thank you all for coming tonight. So today I'm going to basically be talking about the detection of illicit drugs in seized material, with a particular focus on new psychoactive substances, which you may have seen making headlines because they are quite prominent in recent years. But first, what is a drug? So basically, a drug is any chemical or substance you take that will affect the way your body works. So these effects may be physical, such as liver damage or weight loss, or they could be psychological effects, so such as feelings of euphoria or maybe even paranoia. So depending on what type of drug you take, obviously you will find different effects. There are a large number of different types of drugs, and I will start by going through a few that you are probably very common with. The first are a group of legal recreational drugs. So these include things that you are aware of, such as a simple molecule. I had to include some chemical structures, so I've got ethanol there first, and that is obviously commonly found in alcoholic beverages and usually responsible for all the good stories at your work Christmas parties. Then you have caffeine, which is found in coffee beans or tea leaves, as well as chocolate. And lastly, the structure that I've shown is nicotine, and this is the active chemical found in tobacco cigarettes and responsible for the addictive nature of smoking cigarettes. The next group of compounds you would be familiar with, maybe you don't know the chemical structures, but the first one is aspirin. So these are legal medicinal drugs. So aspirin is freely available over the counter to use, and there are no restrictions on its sale. Oxycodone is another legal medicinal drug. However, it is a very strong opiate for pain relief, and for that reason it is restricted and you do need a prescription in order to take this drug. The second one there is Ritalin, which you've probably heard of maybe from The Simpsons, and it's actually a type of amphetamine. So this amphetamine is used to treat ADHD, ADD, and even narcolepsy, but nonetheless it is still a controlled substance because it does have a really high potential to be an addictive drug. So oxycodone and Ritalin are both controlled substances, despite being legal. The next group of substances are your illegal recreational drugs, which I'm sure you are all familiar with. But the first one is Ecstasy. That is the street name for methylene dioxymethamphetamine, which is the compound shown below Ecstasy. And so basically this is an amphetamine type drug, which means it is a stimulant, although it does possess a little bit of hallucinogenic properties, which the user will experience on taking the drug. Normally found in small tablets or pills that are often coloured with logos imprinted. Cocaine is another substance with the chemical structure shown. It's actually taken from the coca plant, so by extracting it from the leaves, you will extract that compound. And basically it is a white powder. However, it does come in another form, such as crack cocaine, which you've probably heard of, and that is the free base form. So by changing something around the nitrogen in that compound, you can create crack cocaine, which is normally smoked. Heroin is a strong opiate, again, with a really high addictive potential, and it is also extracted from a plant, but this time it is the opium that is found in poppy plants. Ice is the street name for the substance methamphetamine. So again, another amphetamine compound, which means it is a stimulant. And you'll notice the structure is very similar to the structure of ecstasy because they are both amphetamines. The only difference is actually this methylene dioxy ring. So ice, or methamphetamine, is the MA in MDMA. The last one is cannabis. So cannabis is the plant, but the chemical responsible for the feelings you get when you take cannabis is THC, or tetrahydrocannabinol. Marijuana is also cannabis, but it's the dried flowers and leaves that you take from the cannabis plant. So why are these drugs illegal? So these drugs have been arbitrarily determined to be illegal based on the effects that you get when taking them. So they look at things like, do you need to take this substance? Is it necessary to take? What are the potentials for becoming addicted to this substance? And also things like, is it safe to use when you're on your own? So things like that go into thought about when you are determining what drugs are illegal. But strictly speaking, if it's listed in the legislation, so whether that is international drug control conventions or federal or state legislations, then that means it's illegal. If it's not listed in there, then it's not illegal. So it asks the question, if a drug is not listed in the legislation, does that mean it's legal to use? And the answer is actually yes, and that was true until recently. So basically what they became called, and you probably heard in the media, was legal highs. So the reason they were called legal highs is because technically they were legal to use. The compounds were not listed in legislation, and therefore they were legal to use. So what happens, they were synthesized in labs similar to this one, normally in countries like India or China. They would then be packaged into fun, coloured foil packages and then sold by your local friendly head shop retailer, and basically sold very cheaply as well. You could also purchase them online from internet marketplaces, which Marie will talk about in her talk, and you could also buy them from regular drug dealers as well. So what are these actual substances? They're called new psychoactive substances. So legal highs is a word used by the media, but the proper word is new psychoactive substances. Now, you have to be careful when using the word new, because it doesn't actually mean it's a brand new, never before seen compound. It actually means it's a newly abused compound, which you'll see when I go through a few examples that you've probably heard of some of them, but they are now being abused when they previously weren't. So the first one I'll go through is synthetic cathinones, which is the one I deal with a lot. So basically it comes as a powder like any amphetamine that you can probably think of, and it does have a similar effect to cocaine or amphetamines. Typically in the media, you probably heard it called bath salts. There was a recent outbreak in the Gold Coast where they talked about flakka. That is also a type of synthetic cathinone. Second one is synthetic cannabinoids, there are a lot of these ones. So that is probably the most amount of MPS substances comes from synthetic cannabinoids. You've probably heard of these as legal marijuana, and again, normally legal highs. A common product that was sold commercially was called spice, and it looks like a herbal material. So it does look like a herb that you are smoking, so you might think, oh yeah, this is natural, awesome. It's actually just a dried herb that has been sprayed with a chemical. And so that chemical is what gives you the effects, not the herbal material that they've used. Phenethylamines, this one is actually a very potent hallucinogen. So you may have heard of 2C, so they come in 2CI, 2CB, etc. or Nbombs. They are very similar to LSD, and often they are sold as LSD. So you may be thinking you're taking LSD when it's actually a phenethylamine. They are far more potent than LSD, so they are normally sold on blotter paper. So this, if you don't know, is blotter paper, so normally you would rip off a square, and that is what you would take. The reason we use blotter paper for phenethylamines is because they are so potent. You only need a few micrograms of the material to get the high. So the way they do that is by putting it on blotter paper. You can only have a small amount on that piece of paper. Piperazines, this is also another powder, similar effect to amphetamines. It was sold as illegal ecstasy, very popular in New Zealand several years ago, also sold as party pills, but recently it's actually had a decline in use and we're not seeing as many piperazines anymore. Ketamine, great example of a newly abused substance. You would have heard of it maybe as a horse tranquilizer because it is an animal anesthetic. And basically, as it's being newly abused, it now comes under the title of new psychoactive substance. So if we start to find it on the street because it is being abused, it comes under this schedule. And lastly is plant-based substances. So one example is kratom, which is the plant shown here. Basically, you can chew that plant and you will get hallucinogenic effects just by chewing the leaves of that plant. So just because it's a plant doesn't mean it's not illegal to use. Okay, so my research focuses, as I said, on synthetic cathinones. So I'm going to go into a little bit more detail on exactly what the hell synthetic cathinones are and how they came about. So they actually all started from a plant again. So this plant is called khat, and it's a little green shrub that is grown normally in East Africa and the Arabian Peninsula. And what the locals do there is they chew the plant. And so they sort of masticate it up into a ball, and they store that ball in the side of their cheek, and then they extract all the stimulant effects from the plant for several hours. So they'll keep that ball stuck on the side of their cheek and just sit there and cruise through. Normally they're sitting down, they're not taking part in activities while they're doing this. And basically the reason they're getting that stimulant effect is from this guy. So this is a chemical, again, chemicals responsible for the highs. This is actually cathinone. So that is how you get the name synthetic cathinones. It's from the chemical cathinone found in this plant. Now, what people, rogue chemists who are making these drugs decided, they saw the potential to alter this chemical structure. So I can change this chemical structure and create new compounds that are not illegal because they're not scheduled. So by looking at this structure in specific areas, bear with me, I know it's chemistry. So what I'm going to do is alter the chemical structure in a few ways. So here I have added on 2 oxygens in a methylene dioxy group. That has created a brand new compound. Maybe I'll add on a fluorine atom. That's another compound. Maybe I'll add on a methyl, then I'll move the methyl around. Each time I'm doing that, you are creating a brand new compound. You can also move over to a different part of the molecule and alter that. Add a few chain lengths, easy. Then I can go over to nitrogen, make a few alterations there. Each time I change something, I'm creating a brand new chemical, a new compound that may have slightly different effects from the one before. And again, if you manage to alter all those 3 things at the one time, you can see that you can make up to 45 compounds just from the ones that I've shown you here. And so that same process can actually apply for all of those MPS shown there, not just the synthetic cathinones. So you can see how there's a very large potential to create a significant number of new psychoactive substances. So you may be asking, how many can we make? There's actually been 644 compounds that have been reported between 2008 to 2015. So these are the ones that have actually been reported to the UNODC, or the United Nations Office on Drugs and Crime. The pharmacological effects, which I have sort of mentioned before, but just to show you in a pie chart, you can see that the stimulants and the synthetic cannabinoid receptor agonists are the most common. So stimulants, you probably have some idea of what they are. They're basically uppers, make you feel more alert, etc. And the synthetic cannabinoid receptor agonists simply means that they behave very similarly to if you took cannabis, okay? That's where we get the word cannabinoid from. And so it has the same sort of effect on the body as taking that. You can also see that the classic hallucinogens, there are a large number of those, and a lot of stimulants also have a little bit of hallucinogenic effect as well. So now you are all very familiar with new psychoactive substances. I will now look at the total number of drug seizures in Australia. So that includes your traditional drugs, cocaine, heroin, methamphetamine, as well as the MPS. So in just the last reported year, 2014 to 2015, there was over 100,000 seizures that were made. So that's a lot of seizures. These seizures are occurring by Australian federal police as well as state police, normally at borders and customs, etc. And that has equaled 23.5 tonnes of these substances are seized. Just in case you don't know how heavy that is, it's actually around about 49 grand pianos. So it's quite heavy. There's a lot of substances that are coming in. That's just in 1 year, okay? You may have heard actually recently, a few weeks ago, we had a very large seizure, almost a tonne. It was just under a tonne of methamphetamine in Melbourne. That was only 2 weeks ago. And these seizures can obviously come in a number of different forms. You can have powders, compressed powders. Obviously, if you have blotter paper that I mentioned earlier, the blotter paper is significantly lighter than a compressed powder, so that will change the differences between the mass or the weight as well as the number of seizures. So now we're looking at drug seizures. So you can see in the image on the left, this is a very large seizure that took place in Colombia. 8.8 tonnes of a substance was seized. So you can pretty much assume that you've got a large seizure like this in Colombia, it's likely to be, no? Yeah, nice, cocaine, okay? However, if you come across a seizure in, say, someone's fridge in the United Kingdom, 150 kilograms of white powder in someone's fridge. You have no idea what that is, all right? So you have to do a sequence of testing to figure out what those compounds are. And this is where I'll start the process of analysis of seized drugs. First step is obviously seizing the material, noting down anything important at the time as well. The second step is what we call presumptive testing or preliminary testing. It can usually involve things like chemical colour tests, like the one I'm holding there, which are easy to use in the field. That's the main point. You want to be able to get a rapid result to tell you what that drug is or what that white powder is in the field. Following from field testing, you need to have that confirmed in a laboratory. So confirmatory testing is really important. Not only does it specify the purity of the compound or tell you what other things are present in the material, but it also gives you a wealth of information about the substance, so much so that you can use it for intelligence purposes. So it tells you the details of what is in that chemical, and Marie will talk to you about chemical profiling of drugs in her talk as well. So what I'm going to focus on today is actually the presumptive testing, because that's what I work on in my research here at UTS. So in particular today, I will focus on chemical colour testing. So they are very portable. As you can see here, there are a number of commercial companies that produce these sort of test kits that you can buy. And the instructions are on the front, the colours are on the front, so you can easily tell. All you do is you squeeze it and it cracks a glass ampule, and that ampule is full of your reagent that reacts with the drug. And you'll see a colour change in the bottom of the pouch. Really easy to do. You can also perform them in porcelain well plates in a laboratory, and that will be an even cheaper way to do these tests because you don't need to buy the commercial testing. They can be selective to the drug class and often to the specific drug as well, but all of the results do need to be reported, so that way you can refer to what compounds will react with a specific test. There are some negatives to chemical colour testing. Sometimes results can be inconclusive. Maybe it doesn't give you a positive or a negative, so then you're left standing there with no idea what the chemical or the substance may be. Another big one is the safety hazards. So often these tests use really strong or concentrated acids as well as harsh chemicals. And I will point out, amongst safety hazards, there's been a recent outbreak in synthetic opioids. If you may have heard of fentanyl and those derivatives, they are really potent substances. So they're 50 to 100 times stronger than morphine, and these substances can be found on the street. So if an officer or someone doing the test in the field has to test fentanyl using these tests, not really ideal to be handling this substance it can be absorbed through the skin, so it's transdermal, it can go through your skin, and they will feel the effects of the drug if they start to handle the compound, if they don't know what it is, because sometimes it does look like cocaine or other compounds. There's also a high risk of false positives. Again, these should all be reported before you are using a specific chemical colour test, which I will go through. And sometimes they are sensitive to the environmental factors, so such as temperature, moisture, etc. So a few common colour tests that are used. So Marquise is probably the most common one. It's a general screening reagent, meaning that it will test for a number of different types of compounds. So for example, it will turn a yellow-brown colour in when it interacts with amphetamine-type compounds, or it will turn a purple colour when it reacts with opiates such as heroin or morphine. Scott's test is the go-to for cocaine. Normally you get a layer of pink and purple for a positive result. Normally just, that's blue, not purple. And then Simon's reagent is normally used to determine or distinguish between methamphetamine and amphetamine, because it only reacts with secondary amines. Okay, so why am I here? So basically, my research is looking at developing chemical colour tests to detect new psychoactive substances. So at the moment, all of the chemical colour tests available don't accurately tell you whether you have an NPS, a specific NPS. So they may react with some of the compounds, but not the whole drug class specifically. So my work looks at, today I'll go through these two classes, synthetic cathinones, which I showed you before, and also the piperazine analogues. So when you are developing a chemical spot test, the main focus is on the molecule that is inside that powder. So this is a molecule of cathinone. Remember from the guy chewing the leaves? This is the molecule of cathinone that has been, they've modified the structure, and there are hundreds of them. They all have a very similar structure, though, that you can work on finding a reaction that reacts with functional groups. I won't go into too much detail, but you have different functional groups present on the molecule, particularly this carbonyl group here and the amine group here. These groups, you aim to find reactions that will affect only those areas, because cathinones are the only compounds that have those functional groups. And so what I did was I came up with a test that uses 3 reagents: copper nitrate, 2,9-dimethyl 1,10-phenanthroline, and an acetate buffer. Basically combining those 3, so one at a time, sequentially, and I found that I was able to form a yellow-orange compound, or product, when it reacted with a cathinone product. So how did I do it? Basically, it's very simple. You have your drug, that white powder is a cathinone, and using your spatula, put it into a porcelain well plate, and then you simply add the reagents sequentially. For my cathinone test, I did need to heat that porcelain plate for 10 minutes in order to see the colour change occur. So once the colour change occurs, then you can, looking at your reference, you always have a reference colour chart, you can see whether there was no reaction or a synthetic cathinone was present. So it is important that you need to run a blank every time you do some of these tests, and you should also run them in triplicate, because there may have just been a contamination of some sort that affected your result. So obviously, when you develop a method, you need to validate it, so that is what I did. So these are some of the results. So purity testing, I found that even at 5% purity, which is very poor, there was still a positive test, or positive result with the synthetic cathinones. Detection limit was 40 micrograms, which may sound small, and it's a really good result for detection in illicit drug seizures, but obviously not for when you're looking at biological materials or drugs inside body fluids. Stability, that is referring to the reagent itself. So how long can you keep that chemical reagent stored in the police officer's car ready to use? And it was very stable. I'm actually still using a reagent I prepared over a year ago. It's running really well. But obviously you would prefer to, prepare a fresh solution before you were doing these tests. And the selectivity was good. There were a few of the synthetic cathinones that showed a weaker colour change than others, but then again, no other compound I tested showed any colour change at all. That was the yellow-orange colour change. And so when I do my selectivity testing, I'm not only testing all the synthetic cathinones possible, but I'm also testing any random white substance that may be used to cut these drugs, and also any white substance that may be used, so like flour, for instance, just random white substances, and also any other drug available, such as heroin, methamphetamine, cocaine, etc. Now on to the second spot test I developed. This one is looking at piperazines, which is a compound that was found in the legal ecstasy. And again, I used 2 reagents, so naphthaquinone sulfonate and also a sodium carbonate buffer. It is important that you do use buffers, because obviously you need to get your compound in the right state before you can do your reaction. And I found it actually produced a red-orange. Picture doesn't do it justice. It's actually a very fluorescent red-orange colour, only in the presence of piperazine and nothing else, the piperazine analogues. This test was actually significantly more simple compared to the cathinone because there was no heating. So you just mix the reagents in, and after 2 minutes you will see the bright colour change if you have any piperazine compound present. And again, these are the method validation. The only difference between this one and the cathinone is the poor stability of the NQS reagent, or the naphthaquinone sulfonate. And so basically I kept it stored in a number of different conditions, and at 35 degrees it actually decomposed or degraded. So I was trying to mimic, say, if you're in a police officer's car, you may reach temperatures of around 35 degrees, so it wouldn't be ideal to keep this reagent on hand for field testing. You would need to use it in a lab so you can prepare it fresh each time. But the selectivity was incredible. It actually only reacted with piperazines, and that was it, nothing else. Okay, so before I finish up, I just wanted to go through a few important things that we hear, so anyone working in the drug research areas at UTS, under the Centre for Forensic Science. So we do a lot of simple presumptive testing research. So other work that I do apart from the chemical colour testing is also looking at optical drug detection using molecular interactions. So it's very different to using the chemical colour test, but the same sort of principle where you want to be able to detect the drug based on its presence. Other people in our research group are working on colour tests for compounds, still MPS compounds such as phenethylamines, and also we have someone, Natasha over here, working on developing some for steroids as well. And in the pre-analytical testing, we have people using the portable instrumentation to detect MPS. And so basically, these portable instruments are really handy because they provide more information than a chemical colour test ever could, but they are able to be used at the field. Very ideal. And we also have students working on detecting illicit drugs through packaging. So that means not even having to open up the cardboard box or the parcel that it came in, but we can actually point and shoot using Raman spectroscopy and go through and detect these compounds. And lastly, we have a lot of people working on confirmatory testing. Now, this is really important. So Daniel Pazin works on developing non-targeted screening methods. So what does that mean? Basically, each time a new compound comes out, we don't know what we're looking for. We don't know these new compounds when they come out. So Daniel Pazin and also Josh work on developing methods to be able to detect things that we're actually not looking for. So it's a very ideal situation for when you're in a forensic laboratory, because you are able to tell if there is a drug in there, even if you're not looking for it. And we have Josh is also working on chemical profiling of synthetic opioids, which is what I talked about before. These are the really potent ones, stronger than 50 to 100 times stronger than fentanyl, and then some are even more potent than that. And so by chemical profiling, which Marie will talk about again in a moment, helps us to look at where they came from. So in answering this final question, are we fighting a losing battle? So basically, detection is a very crucial first step to fighting this battle. You can look at it from ways of preliminary testing, which is what I work on, to provide a drug identity. You can also look at confirmatory testing that provides information-rich detail that you can use in profiling these sort of drugs, and that will give you even more information. So basically, by doing these research that we do at UTS and combining them all together, we have a better stronghold in this fight, or this battle. So thank you.
Thank you, Morgan, for a really exciting talk. I might just make a little comment. I realize that the Simpsons are pretty exciting people, because not only they can predict the result of the American election, but they make their way to every single Science in Focus night. I think there was some Simpson in the last one with Steve Woodcock on statistics. Next speaker, obviously, it's Marie Morelato. So Dr. Marie Morelato is a Chancellor's postdoc research fellow at the UTS Centre for Forensic Science. And at the moment, she's developing an exciting portfolio of projects in a new field that is someone reshaping forensic science, which is called forensic intelligence. But it also includes researching the use of illicit drug data from an intelligence perspective. And that's the main theme of tonight. Marie's research involves the fusion of data coming from projects that look at the illicit drug problem through different angles, including crypto markets, illicit drug seizures, illicit drug in wastewater, and data from governmental sources. She's also interested in other areas dealing with organized systems, organized crime, security, and so on, for which this approach can be adapted and implemented. Marie has a bachelor and master degree in forensic science from the University of Lausanne in Switzerland and completed a drug intelligence PhD at UTS. The masters were in Lausanne, but the PhD was at UTS in 2015. She's also worked as a forensic scientist in Switzerland and in Australia, including completing a project on gunshot residues in collaboration with UTS, the Australian Federal Police, and many other partners along the way. So please welcome Marie.
Thanks, Claude, for this introduction, and thanks everyone for coming along tonight. It's very nice to see that so many of you are interested in the topic of illicit drugs, hopefully for the right reason. So as Claude mentioned, I'm currently doing my postdoctoral fellowship here at UTS in the area of forensic intelligence, and how do we apply forensic intelligence in the context of illicit drug. So tonight I'm going to introduce the concept of forensic intelligence, explain what it is, because it might still be a concept that some of you might not be very familiar with, and then how to apply that to understand the problem of illicit drugs. So, the forensic scientist, what does he do in his everyday life? So, I'm just going to take the example of DNA because it might be a trace that you might be more familiar with in comparison to illicit drugs. So when a crime happens, usually the crime scene officer or the forensic scientist goes on the crime scene. He collects whatever he thinks that is relevant for the case, and in our case here, it's a trace which is blood. And then they analyze the blood to obtain a DNA profile. Once the analysis is done, then it can be compared to a database. And sometimes there is a hit in the database, so that leads to the arrest of a suspect. And finally, the evidence is presented in court. So when a second case happens, a similar process is conducted. So that means that in the traditional role of forensic science, both cases are treated separately. So let's take the same example, but let's say that it's a burglary, 3 different burglaries. So the crime scene officers will go on these burglaries, will collect whatever he thinks relevant for the case, analyze these traces to obtain the DNA profile, but unfortunately in these cases, there is no suspect. So what do? Should we just stop here? And then just wait till maybe the next generation of DNA will come out in the next 10 years? No, what we could do is we could use these traces and compare them to each other. And when we do that, we can see some similarity. We might see some similarity. And in these 3 cases, these 3 DNA profiles that were collected on different cases are related to each other. That means their similar DNA profile was collected in these 3 cases. So that's interesting. Obviously, we still don't have a suspect, but we have a series of crime that was perpetrated by the same offender. So once we go a step further, and we try to map these cases on the scene map, for instance. And what is interesting is that all these burglaries happen in the similar region in Sydney. So using that information and also the circumstantial information of each one of these cases, we manage to localize and identify a suspect. So previously, the circumstantial information on each one of these cases was not enough to identify a suspect, but now combining the information from each one of these cases, we manage to identify a suspect. So a suspect is arrested. And then when we look at the number of burglaries according to the week which had a similar DNA profile, that's the kind of chart that we can do. And what is interesting is when the suspect was arrested, no more burglary were happening in this region. So you can see by using the traces more collaboratively, we manage to disrupt a criminal activity. Then we can even go further, and then instead of treating only these cases that were related to each other through the DNA profile, we can analyze all the burglaries that happened between May and August 2016, for instance. And what we observe is that the majority of these burglaries occurred between 5 p.m. and 11 p.m. So that's an interesting information. And when you look at the time frame, it's between May and August. So that means in Sydney, it's winter time. So the sun sets obviously around 5 to 5:30 p.m. So when you are at home, usually you will switch on the lights. And if nobody's at home, usually the light will be switched off. So the burglar, they usually don't want any contact with the person who is inside the home, so obviously he might just commit his burglary between 5 and 11 p.m. So that's an important information because not only it helps police or law enforcement agencies to maybe allocate their resource in a more efficient way, but it also informs the general public that maybe at 5 p.m. you might want to have an automatic switch on of your lights, so just in case, so that you don't want to have a burglar in your house. So that's what forensic intelligence is about. So instead of treating each case separately, we treat them as a whole to obtain knowledge about a criminal phenomena. So obviously tonight we're not here to talk about DNA, neither about burglaries. We are here to talk about the problem of illicit drugs. So how do we apply the concept of forensic intelligence to obtain a better knowledge about the illicit drug trafficking and illicit drug consumption? So tonight, as Claude mentioned in his introduction, I'm going to talk about 4 different sources of information, which are the profiling of illicit drugs, that also Morgan mentioned in her presentation, wastewater analysis, crypto markets, and surveys. So don't worry if you don't know yet what they are. I'm going to explain what they are in the following slides. So the first one is the profiling of illicit drugs. So why do we use drug profiling, and what is it? So I had the same accent as Claude, and we both come from Switzerland, so I had to use an example from Switzerland, which is chocolate. So hopefully you had a lot of chocolate during the Easter break. So what you can see here is different brands of milk chocolates. So what they have in common is that they're all milk chocolates. But if you look at their behind, at the back, the package, and you look at the composition of these different chocolates, and let's take an example with the sugars, the sugar content is different from one brand to another. So that means that we could potentially use that information to know if 2 different milk chocolates come from the same factory or have the same brand. And it's very similar with drug profiling, but obviously you don't have a label at the back, but when you analyze these drug seizures, you obtain a chemical profile. And it's very similarly to the chocolates. If you use this chemical profile to compare the seizure to each other, you might know if they come from a similar clandestine laboratory. So when we do that, okay, this chart looks a bit scary. It seems that it's a spider web, but it actually tells us some information. So if we analyze all this drug seizure and we see if there is any links between them, that's the kind of chart we can obtain. So this is just an example of heroin, but it could be done with MDMA or cocaine, whatever drug you want. And it tells us the structure of the drug market. So you can see this little dot here. That means it's a seizure that is not connected to any other seizure through the chemical profile. But then you've got this massive cluster here in the middle, and that means that a lot of seizures that are connected to each other. So that's actually help us identify organized crime group, and it's this massive drug cluster is probably an organized crime group. So drug profiling is actually helping us to understand the drug market, but also to target the resources, the police resource, in a more efficient way, since they can probably target these massive cluster here. So unfortunately, all of these sources of information have uncertainties related to them, and the uncertainty that is related to profiling of illicit drug is the fact that it's based on what is seized by law enforcement agencies. So it doesn't represent all what is on the streets. So let's go to the second source of information, which is wastewater analysis. So you might have seen in the news recently there was a big report that was published, and in this big report they analyzed wastewater in a lot of different states and territories in Australia, actually in all the states and territories in Australia. But why do we use wastewater, and what information it can give us? So if you smoke a joint, for instance, the smoke will come into your lungs, and then it will be absorbed into your blood, and then distributed into your body, and usually into your brain, because obviously that's where the effects of the drug come from. And then it will be decomposed, because it's like food. So when you eat food, then your food has to be decomposed in smaller compounds in order to be excreted. And it's very similar with illicit drugs, but these smaller compounds are called metabolites. And once it's metabolized, then it is excreted from your body. When you go to the bathroom, you flush the toilets, and the water goes towards a sewage treatment plant, which is just the picture at the bottom there. And so if we analyze the water coming into this sewage treatment plant, we will obtain an estimation of the illicit drug consumption of this area, of the area where the sewage treatment plant is, anyway. But yeah, so you will obtain an estimation of the consumption. So we did a bit of a study last year with a student here at UTS, and we analyzed 3 different locations in Sydney, in the Sydney region. And what we observe is that methamphetamine is quite highly consumed in Sydney in the 3 different locations. And then when we compare that value to European studies, so there is a lot of studies that are conducted around the world, and this is just one of them that is conducted in a lot of cities in Europe. And when we compare the methamphetamine level that we obtain in Sydney to the one in Europe, what we observe is the Sydney level of methamphetamine are quite high. So obviously that's just an example. It's the example of methamphetamine, but you could do that with cocaine, heroin, to look at all of them. So wastewater is also important because it gives us an objective estimation of drug consumption in a particular region. The uncertainty related to it is the fact that, as Morgan mentioned, it's sometimes very hard to know what we are looking for. And the new psychoactive substances, for instance, we actually don't know how they metabolize in the body. So in order to look for metabolites, it's really hard. So that's the source of uncertainty. Then the third source of information that we are also using is crypto markets. So you might have heard of Silk Road, the shutdown of Silk Road in 2013 by the FBI. If not, that Silk Road was a crypto market. So don't worry, I'm going to explain what they are. So when you go on the internet, usually you go on the surface web. So that means that they are the pages that can be found using typical search engines such as Google. So it's mainly what you use every day. So that's a very small part of the internet. And then you've got a 96% of the internet, which is called the deep web. So that's these web pages that search engine cannot find. So for instance, if you think about a library website or a paywall where you have to enter a username and a code to enter it, that's found on the deep web, so not everyone can access it. And then you've got a really small part of the deep web, which is called the darknet, which is the encrypted part of the deep web, intentionally hidden and only accessible with special software, such as Tor, if you have heard of that. So crypto markets are found on the dark net. So if you think about eBay or Amazon, for instance, it's exactly the same, but instead of selling legal goods, it is used to sell illegal goods, and mostly drugs. So this picture is just an example of one of the crypto markets. So as you can see, you've got different listings, and then you can click on them, very similar to eBay. So why do we use crypto markets, and what information do we want to extract in order to analyze it? So if you have a listing, so in this case it's MDMA, then what we are interested in is the type of illicit drugs, the price of the illicit drugs, so that's in Bitcoins, so it's just the cryptocurrencies that is used on crypto markets, but it's really it's related to US dollars or Australian dollars, so you can convert it pretty easily. And then you've got the shipping country, so where is it shipped from? The shipping destination, so where is it shipped to? And then finally, description of the illicit drug. So that's what is displayed on the browser. And obviously, we cannot really use this information straight away. What we have to do is to extract that information for every listings on crypto markets. And in order to do that, we just transfer the information into a usable format. Once we have this usable format, we can analyze it. And one thing we can do is called the trafficking flow. So I know this graph is also a little bit scary, but I'm going to explain what it tells us. So you might have seen actually this kind of graph for immigration flow, but usually it's from immigration from one country to another. It's very similar, but instead of immigration of people, it's immigration of illicit drugs. So I'm just going to show you the example of the Netherlands here and Germany. So what you can see here is that the Netherlands and Germany mainly export illicit drugs, so it goes from the Netherlands to worldwide, to European Union, and worldwide except Australia. Whereas if you look at Australia, it's mainly domestic. So that means that sellers in Australia mainly sell to Australian customers. So there is different reasons that can explain that. One of them might be the very tight control at the border, but also the higher price of illicit drugs in Australia. So then we can do other things as well. We can, for instance, compare the crypto markets, so the virtual market, to what is seized by law enforcement agencies. So when we do that, if we look at all the listings that are offered on crypto markets, we can see that cannabis is the one that is most sold on crypto market for Australian, as an Australian perspective. Then you've got ecstasy and MDMA, and then methamphetamine. And if you look at your law enforcement seizures, which is on the right-hand side, then you can see that the drug most seized is also cannabis, followed by amphetamine-type stimulants. And amphetamine-type stimulants include ecstasy and MDMA, methamphetamine, and amphetamine. And you can do that for all of them. And what we can see is that the virtual markets, so the crypto markets, and the traditional markets are connected to each other, and they don't seem to be two separated markets. So crypto markets are also important because, especially nowadays when internet is more and more used and everything, so it might be a new source of trading illicit drugs. So it is important to do research in this area and also to show that both markets are actually connected to each other. But the uncertainty is obviously we rely on data that is told by sellers, so that might not be completely reliable. The last source of information that I'm just going to briefly talk about is surveys. So there is a lot of surveys that are conducted every year in Australia or around the world. And the one I'm just going to focus on is the National Drug Strategy Household Survey, which is conducted every 3 years. So that's the results of the 2013 one, just because the 2016 is not out yet. So in this graph, what we can see is what are the drugs that are consumed by the general population. So usually what they ask in this survey is, have you ever consumed any illicit drug or cannabis or whatever drug that are here on this graph. So what we can see is that the most consumed one is cannabis, and then followed by pharmaceutical misuse, and so on and so on. So surveys are also important, but unfortunately, there is a bit of subjectivity on them, because it depends on if people are willing to actually answer the question. So that leads me to my conclusion, and similarly to Morgan, I've got the same question. Are we fighting a losing battle? So obviously it all depends what battle we are talking about. So in our case, the battle is to try to understand drug markets using different sources of information. So in my opinion, we are not fighting a losing battle. And I hope by showing you these 4 sources of information that all have the uncertainty, but we think that combining them will help obtain a better knowledge about the illicit drug trafficking. And this, in turn, will better inform the policymakers to make the right decisions, but also the community, because it's more informed. Then it will also help disrupt criminal activity, better allocate the resources, and better evaluate the risk. And finally, which is quite important, is even though tonight we only talked about illicit drugs, a similar process can be used for any type of traces. So weapons, smuggling of migrants, or false identity documents, whatever trace you want. So that's why we think that this approach is very important. So that's how I'm going to end up my talk. And I just wanted to acknowledge a couple of people that helped developing the talk and also helped me in my research. And obviously, thank you for your attention.